In chapter 13, we start discussing chemical equilibria, which is going to be the topic that consumes most of our time for the rest of the quarter. So in this first section, we just establish a definition of what chemical equilibria is and work through looking at a few of the basic properties of systems at chemical equilibrium. So chemical kinetics, which we were studying in chapter 12, describes how fast a product is produced. So when you want to know how quickly something is moving from reactants to products, that's what we call a kinetics problem. Chemical equilibrium properties describe how much product can be produced from a given amount of reactants. So in a sense, they are related to stoichiometry. So previously we had used stoichiometry to calculate the amounts of products that could be produced from a given amount of reactant. And we would say something like this. We would say that if we have a reaction where there is a one-to-one relationship between reactants and products, then the number of moles of my reactant will just be equal to my number of moles of product. In these stoichiometry type calculations, what we're assuming is that the reverse reaction is not occurring. At least we're assuming that the reverse reaction is not occurring to any significant extent. And we know from our studies in chemical kinetics that the reverse reaction is frequently occurring and will become more and more important as the concentration of the products builds up. So when we were discussing reaction rates earlier, we noticed that sometimes the reverse reaction is significant. And we had these problems where we were looking at reaction mechanisms where we had a fast first step and a slow second step. And what would happen is the concentration of our product from the first step would build up because it was only being consumed slowly in the second step. And as a result, the rate of the reverse reaction would become more and more important as the concentration of this guy built up. Now, of course, as we're producing C, and we're doing this quite quickly, the concentration of A and B are decreasing. And what that means is that the rate of the forward reaction will be decreasing at the same time as the rate of the reverse reaction is increasing, and eventually we arrive at a scenario where in the first step the reverse reaction and the forward reaction are occurring at equal rates. So what happens is that the rate of the forward reaction ends up equaling the rate of the reverse reaction. So a system where the forward and reverse reaction are occurring at the same rate is described as being at chemical equilibrium, and we can indicate that with the double-headed arrow. So here we have a generic reaction. Reactants are being turned into products, and products are being produced. And what happens is that the rate of the forward reaction decreases with time because we are consuming reactants, and the rate of the reverse reaction increases because we are producing products, and eventually they become equal, and when they do, we say that the system is at equilibrium. So once a system reaches equilibrium, the amounts of products and reactants will remain constant because the rate of production of our products is equal to the rate of consumption of our products. So therefore, the amounts of things are just not going to change. Now, there's a lot going on at a molecular level. Particles are still being converted from one type to another. It's just that there's no overall change in concentration in the amounts of products and reactants. So previously, when we were talking about the idea of vapor pressure, I'd mentioned the concept of like a parking lot that is full. So the parking lot is full and people are lining up to get in, and you're like wondering, what are they doing? There's no spaces. But what's happening is people are leaving, people are arriving, Because those processes are occurring at the same rate, one in, one out, the parking lot always remains full, but it's always different cars that are in the parking lot. It's a similar idea when we consider the physical equilibrium of vapor pressure. What happens in vapor pressure is you take a liquid and you seal it inside a container, and you can see we've noted the level of the liquid right there. And initially there's very little vapor above the liquid, and particles are leaving the liquid quite quickly because there's quite a large surface area of the liquid there, and there's only a few particles in the gas phase, and so not many of those return per second to the liquid. So after a while the level of the liquid drops, and now we have more particles in the gas phase, and the rate at which particles return from the gas phase to the liquid will increase. Eventually you get to a point where the rate of evaporation equals the rate of the return of the gas phase particles to the liquid, and the level of the liquid doesn't change, and the pressure of the vapor remains constant, and that's what we refer to as the vapor pressure. The vapor pressure of the liquid is the partial pressure of a liquid when it is in equilibrium with its vapor, and that means that the liquid is leaving just as quick as the vapor is returning to the liquid.